There are many development boards in the world, each of them having specific features and having a different or similar field of application. In this movie, I will compare two of these systems, the NavQ and the Raspberry Pi 4. The comparison will be mainly from the point of the computational power required to sustain a human detection algorithm from a video stream. Before moving on the proper analysis of the system's performances, let's analyze the two processors datasheet. Both of them are from the ARM v8A architecture class, but the NavQ system on chip has a Cortex A53 and the Raspberry Pi 4 has a more powerful Cortex A72. The Cortex A53 processor is the one that exists inside the Raspberry Pi 3 development board. Both processors have the same number of powerful cores and are on the same number of bits. We notice that the NavQ has a supplementary Cortex M4 processor. The most significant differences is in the processing power. That is double on the Raspberry Pi system, 4.72 versus 2.24. The NavQ system has a small advantage in working at a slightly higher frequency. But the L1 cache, the L2 cache, and the pipeline depth are to the advantage of the Raspberry Pi 4. The Raspberry Pi 4 also has an out-of-order execution unit that is missing on the NavQ system. They have the same amount of memory, and I know that the Raspberry Pi system has more memory, but the one on which I will do all the tests has 2 gigs of memory. The biggest difference is that the NavQ runs a 64 bits Ubuntu operating system, but the Raspberry Pi runs a 32 bits operating system. Okay, based on this information, the feeling is that the NavQ system has no chance in this competition with the Raspberry Pi system. But is that so? Let's see. You'll have a big surprise. The benchmark program is here an application developed for the NXP HoverGames Challenge 2 contest. It is only the basic application without any communication with the flight management unit or other functions required by the contest. The Python application uses an input video file, which is a short movie of only 6 seconds, in which a person is running through a forest. The movie was recorded by a drone that follows him. The Python application was developed based on the OpenCV library and OpenVINO toolkit. It can run the human recognition algorithm entirely on the ARM CPU or supported by the Neural Compustic 2. To switch between these two working modes, I used this argument. Now the human detection algorithm is running with the support of the Neural Compustic 2. The detection is done based on the MobileNet single-shot multi-box detection network, a deep neural network implemented using the Caffe framework. I will evaluate both system detection speed using the number of frames per second able to be obtained by the detection algorithm. This parameter is returned by the application together with the total processing time. Mainly because the NavQ is a headless device, we have the last argument that allows us to point out the place where the result will be saved and after that analyzed. Let's test the Raspberry Pi system performances with the graphical user interface started, and after that I will go to the command line interface. In this way we will be able to evaluate how much of the system power is stolen by the graphical interface. The first test will be done running the deep neural network only on the Raspberry Pi CPU. The output folder is empty, and the result will be written there. So let's start. The first thing that can be noticed here is that this process is clearly a slower one. The MobileNet single-shot multi-box detection network requires around 2.3 gigaflops, and it has around 5.8 million of parameters. More of that, the main program is running on the second core, and the writing process is running on the third core. In this way, the processing performances of the recognition algorithm will not be influenced by the writing process. The algorithm finished, and we get around 1.3 frames per second. And right now, I will download the resulting movie from the Raspberry Pi to my computer, and here we'll play, and we'll see that the recognition process is working perfectly. The second test will be done running the deep neural network with the support of the Neural Compute Stick 2. I will delete the previous movie, and in this mode the output folder is empty once again, and here will be write the result of the human detection process. Okay, we started. The process ended, and we can see that using the support of the Neural Compute Stick 2, we will get 8.9 frames per second. And in the similar mode, we'll download the file to the personal computer. And we'll start to play it. In the same mode, the recognition process is very good. And right now we'll prepare the following test, and we'll test the performances of the Raspberry Pi system without graphical user interface from the command line. Right now we are once again on the Raspberry Pi system. The connection is made through a SSH session interface, but this time it is a headless system without graphical user interface, and here I will repeat once again all the tests. In this session, the first time I will execute the deep neural network only on the Raspberry Pi CPU. Analyzing the results, we see that the performances are the same as the one previously obtained. To prove that the system was able to process correctly the input data stream, we'll do that in the previous situation. We download the movie from the Raspberry Pi system to the personal computer, and after that we'll run. And you'll see that the system is able to recognize correctly the human. In the second test, I will use the support of the Neural Compute Stick 2. The result is a little better than the result obtained with the graphical user interface. 9.21 versus 8.19 frames per second. Now I will repeat all the tests previously done on the Raspberry Pi on the NavQ system. First, I will start the recognition process on the CPU and we will see the results. The idea to run the recognition process on one core of the system and the results writing process on another core is based on this. One moment, I have here opened a new SSH session, and now we will analyze the CPU load. You see that are two Python processes that get almost all the core processing power, and it will be unwise to put them on the same core. But right away I will show you something unexpected and unimaginable that will blow your mind, but now let's wait for the results. The performances are very close. 1.20 frame per second on the NavQ system and 1.29 frame per second, if you remember, on the Raspberry Pi system. These results will be discussed shortly. Right now, let's change the Python program, removing all the code associated with the process affinity. First, we have here and here. Write and quit. Right now, I will run once again the recognition process. The CPU load for one process is 259%, and you'll see that this process is jumping from one core to another core. Oops. And the results will be, surprise, surprise, we got 2.63 frame per second, more than double. Okay, this problem of process affinity is almost on all the analyses previously done. But in the end, I will show you all the updated information. Let's start the last test. Running the recognition process on the Neural Compute Stick. But unfortunately, I get the following error that I could not solve up to now. But we have plenty of data to make a performances comparison between the two systems. In the end, I presented here, together with the CPU's parameters, the performances obtained by the human recognition system when the process's affinities were configured from the program and when the operating system sets the process's affinities. The first observation is that this application performance differences between the command line system and a desktop system with graphical user interface are very small. But the most shocking conclusion is given by the fact that we have two different systems. One of them, the Raspberry Pi system, is more powerful than the NavQ system, but the human detection performances are very similar. So we have here 1.2 frame per second versus 1.29 frame per second, or 2.62 frame per second versus 2.65 or 2.75 frame per second. These small differences are given, in my opinion, by the fact that on the NavQ system, the OpenCV and OpenVINO libraries are built on 64 bits. On the Raspberry Pi system, all is working on 32 bits. This was all. If you enjoyed, I am sure that you'll know what to do. Thank you very much.